All right, so we're at problem 10 of the final exam practice. And with each one of these parts, A, B, and C, we want to determine whether the series that we're given is absolutely convergent, conditionally convergent, or divergent. Let's focus on part A for right now. So we have the series n equals 1 to infinity of the natural log of n over 2n plus 1. So we always want to think the first thing about our series, because it's the easiest thing to check, is what is the limit of the terms as n goes to infinity. So in this case, we're looking at our terms are equal to natural log of n over 2n plus 1. Right, and we want to know what is the limit as n goes to infinity of a sub n. Of course, this is the limit as n goes to infinity of natural log of n over 2n plus 1. And so since natural log is continuous at the limit of the inside portion, let's just take the limit of the inside portion. We'll see that it has a particular value. And we know that natural log is continuous at this particular value, so we can actually pass the limit through, and then we'll have the limit of this sequence, and we'll see what it is. All right, so either way, we want, first of all, the limit of n over 2n plus 1, so just the stuff on the inside of the natural log. And so we see that our numerator is blowing up, our denominator is blowing up, so we might want to use L'Hopital's rule, but actually that's not exactly necessary in this case because we can get away with algebra. So we'll just divide both the numerator and the denominator by n. So 2n plus 1. So we're going to do 1 over n divided by 1 over n and multiply our terms by that. And so, of course, in the numerator, we'll end up with a 1, just n divided by n. In the denominator, we'll end up with 2n over n, so just 2 plus 1 over n. Okay, and either way, we know that 1 over n, this limit goes to 0, of course, as n goes to infinity. And so now we can just take the limit of the numerator and denominator, and we see that it's equal to 1/2. Okay, natural log is continuous at the input 1/2. So the limit that we have for the whole entire expression, right, we just took the limit of the inside there, is that this is equal to natural log of 1/2. Right, so we can just pass the limit inside. Okay, but natural log of 1/2 is not equal to 0. And so we have, by the test for divergence, that because the limit of the terms is not equal to 0, then our series is going to diverge. Okay. All right, so part A, our series is going to diverge because it doesn't pass the test for divergence. Okay, moving on to part B. So we have the numerator is 1 plus 2 to the power minus n. The denominator is n squared plus 1. So you're kind of thinking that the numerator is like 1 plus some small term. So either way, 1 plus 2 to the minus n over n squared plus 1. I just want to think that these this term for large values of n, I kind of want to think of what it's close to. And so what I mean by that is in the numerator I have 1 plus 2 to the power minus n. 2 to the power minus n is very small. It's very close to 0 for large values of n. So this numerator is going to look like 1 for large values of n. In the denominator I have an n squared plus 1. And of course for large values of n squared is going to dominate this term 1. So the denominator will look much like n squared. And so the terms of our series are going to look a lot like 1 over n squared for large values of n. And so we're going to expect this series to converge. And so that's what we're going to try to show, is that the series converges. So we know that 1 plus 2 to the power n over n squared plus 1. So first of all, we know that the numerator is 1 plus some positive number. Okay, so if it's going to be greater than 1, which either way, that's not going to help us very much. Okay, but if we notice that 2 to the power minus n is always less than 1 when n is greater than 1, because our n just runs from 1 to infinity. So 2 to the power minus n is less than 1. So I can write the numerator as less than 1 plus 1, because this number is less than 1, and so I can just write it as 2. Okay, and the denominator is n squared plus 1. And we also know that n squared plus 1 is, of course, larger than n squared in general. And so this is actually a smaller number than 2 over n squared. Right, and this is true for all values of n. And what do we know about a series with terms 2 divided by n squared? Well, it's a p-series. It's 2 times a p-series with p greater than or equal to, with p strictly greater than 1 equal to 2 in this case. And so this is going to be a convergent series, and we showed that this convergent series, all of the terms are greater than the terms of the series that we were looking at. So we know that 1 plus 2 to the power minus n divided by n squared plus 1. This is, of course, less than or equal to 2 divided by n squared for all n. And so we can sum each side. Because this is a convergent series, right? This is a convergent series. Because it's a p-series with p strictly greater than 1. Right, p is equal to 2 in this case, so p is equal to 2. Okay. All right, and so since we showed that our series is less than the value, than the sum of a convergent series, then the series that we're originally dealing with is also convergent. And in this case, since all of our terms are positive, we'll just say that it's absolutely convergent, because absolute convergence and convergence are one and the same thing here. All right, so that finishes up part B, and we're going to go on to part C in the next video.